So so the recording will be shared on the YouTube channel. You already know the link to that. So let me just start my discussion. Okay. So earlier we talked about search algorithms, and the last search algorithm we talked about was A star algorithm. Today we'll start the third module for the course, and this would be the final module because we don't have enough time to actually cover the other things. So I'll finish with this module, which is an introduction to a couple of machine learning algorithms. So the first machine learning algorithm that we'll be discussing is decision tree. Now, decision trees primarily is a data representation in the form of primarily in the form of rules, and this conversion of data into tree format, and we are strictly talking about trees here. We are not talking about graphs here. So it's a tree representation of the data. Now, the data representation is such that each branch of the tree represents a rule. Okay. So each branch of the tree would represent a rule in this case. Okay. So let me just give you an example here. So on the right hand side of the slides, you see that we have a decision tree representation. And what is this decision tree about? This decision tree is primarily about finding whether a person is fit or not. So you can see decision trees as a sequence of questions that you ask in order to decide your output. So in this particular case, we want to decide whether a person is fit or not. So therefore, we'll be asking some questions. So the first question is, for example, this decision tree represents that the first question is that you ask about the age of the person. Is the person less than 30 years? And answer, if it is yes, then you follow the left branch. If the answer is no, you follow the right branch. So that's the first question that you ask. And if it is not enough to decide whether a person is fit or not, then you ask a subsequent question, a second question. And the second question in this particular case, if you follow the left branch, then the second question you ask is that whether that person eats junk food or not. And if the answer is yes, then you can reach a decision and which says that the person is not fit. And if the answer to the second question is no, then you can say that the person is fit. Okay. So here we have got some rules, and these rules primarily are representing a sequence of questions. This sequence of questions is represented in a tree format, which is given here. Okay, so the terminology that you use in trees is exactly the same which you use in decision trees. For example, this node, which is your starting node, that is representing the root node, and we also call this as a decision node. Then the second nodes here, which are represented in different color, that represents the second decision node, and that is basically the second question. And then you have the leaf nodes here, which are representing the results. Okay, the final answer. So in this particular case, you ask just two questions, and answers to those two questions would lead you to the final answer, which is whether a person is fit or not. Okay, so this is representing what? This is representing rules. The rules are represented in the form of a tree, and because you are deciding based upon this tree, therefore you call this as a decision tree. Okay, is this thing clear? Is there any question about this? So what you can actually detect out of this is that each branch is representing a rule. So for example, this branch is representing rule 1 for decision. That's representing another rule. This is representing another rule. This is representing another rule. Okay, and that's why we call it a decision tree. So, so what are those things that help you decide that if you are given two decision trees, so you have got one decision tree and you have got another decision tree, if you want to, and they are performing the same type of task, but the decision nodes are having different variables. For example, one decision tree starts with saying that you ask about the age first, and then you ask about the junk food. And on the right branch, you ask about the workout. So you see on the left branch and on the right branch, you are asking different questions. Okay. Now, you can have multiple decision trees that could perform the same task. For example, the task here is to identify whether a person is fit or not. Okay, here the first question that I am asking is about age. But I can also start by asking about the workout. I can also start by saying that, okay, is the person doing workout or not? And then I can ask about the age on any of the other branches. Okay, so then I can ask about the age. This is also a possible thing. I can actually do this also, rather than doing what I'm suggesting here. So what I'm suggesting here is that you ask about the age followed by the workout, and it could be the other way around. You can ask about the workout first and then about the age. That's also a possibility. Okay, but this will generate a problem. The reason for this problem would be that you will not be some of the trees that you may develop, they may be less accurate in predicting whether a person is fit or not. Okay, for example, this tree which I'm showing here, this may be more accurate compared to this type of a tree where you are asking a different question. So accuracy of a tree, that given an instance, how many times the tree correctly predicts whether a person is fit or not, is what we call as the accuracy of the decision tree. So in both cases, if you ask the age question first, or you ask the workout question first, the accuracy of the decision tree may be different. Okay. And we'll now see in a while that how a decision tree is developed. Now, in order to develop a decision tree, the first question that you have to solve is that what should be the first question that you need to ask? Should you ask about the age of the person or should you ask about the workout? What question should you ask? And then once you have asked your first question, then what should be the second question? Right? And what should be the third question? This decision tree, which I'm showing you here, is only asking two questions. So here I can actually say the questions that I could actually ask you is that, okay, I have asked the first question about the age, then on the left branch, I am asking about the food, and on the right branch, I am asking about the workout. Why is that? Why should I not ask about the workout on the left branch? If the age is less than 30, why should not I ask workout question? I'm asking the food question on the left branch, this branch. So I'm asking this question. Why not the other question? Now that's an important observation. And there is a theory behind this. There is a way of developing a decision tree that will answer this question. That why is this sequence of questions? Why can't I ask a different sequence? Who determines this sequence? Okay. Now, is this thing clear? Shall we move on? Okay, wonderful. Okay, so now the important thing here is that what should be the sequence, of who determines the sequence? Who determines this sequence? And the answer lies in on this slide, which says that okay, we will try to find out those variables or those questions that reduce the noise in the system. Okay, and let me just explain what noise in a system means. Okay, let's suppose I've got a basket, and in this basket I have got some, let's say, some shapes. So I've got triangles there. There are three triangles there, and there are, let's say, three circles in this basket. Okay, so if I ask you, what does this basket contain? Just one answer. Whether it contains triangles or whether it contains circle, what will be your answer? Will you be able to decide that what does this basket contain? No. Good, Jihad. And Sanad and Ahmed, what do you say? Okay, so the indes. Okay, why can't we decide? Because the circles and the triangles are equal in equal number. That's why we cannot decide. Let's say if I add, yes, exactly. Yeah. So if I add more circles here, so let's say I have added two more circles. Now, if I ask you that what is this basket containing? So you can actually say that, okay, majority present in this basket is of circles. Therefore, you can label this basket as the basket of circles based on majority vote. There will be error here because this is a basket that does not completely contain circles. It also contains some triangles, right? Yes. So majority, because the majority is of circles, therefore I'll say that this basket, I can label this, that this basket is of circles. Okay. On the other side, let's say if I've got a basket that contains all triangles. Okay, and if I ask you what is this basket, what should be the label for this baskets, and you can simply say that okay, this basket is of all triangles. I can label this basket as triangle basket. And similarly, I can have another basket in which you have all circles, right? And if I ask you that what should be the label for this basket, you can very easily say that, okay, this is the basket of circles. So this is absolutely clear. This is absolutely clear. There is no doubt about these two baskets. So that means there is no indecision. We call this as indecision. There is no indecision. Indecision means that you are not able to decide. So here you are able to decide in both cases, in this case and in this case, that what is this basket consisting of. Here, there is some indecision, but because the majority belongs to circles, therefore I label it as circles. Okay, so here I have got 100% decision. I'll label it as 100% decision. Here I have got 100% decision. Okay, and here it is less than 100%, but greater than 50%. Because one class or one object is in majority, therefore I'll actually say that this basket belongs to that majority. And if there is no majority of any class, for example, if there are two triangles in this and there are two circles in this, then I will say that, okay, this is completely indecision. I cannot decide. This is like 50-50. I cannot label this. I cannot label this as a triangle. I cannot label it as a circle. The reason is that both of them are equally present there. So out of these four different scenarios, there are two scenarios in which I am 100% sure about the label of the basket. There is one scenario in which I am absolutely not sure, which is this scenario. And there is one scenario in which I am relatively sure because of the majority of the circles. And I can say that, okay, because majorities of circles, therefore this basket belongs to circles. Okay. Now, this is what we call as identifying the noise in the system, or we use the term entropy. So when there is a mix, when you are absolutely sure about the label, you say that the noise is zero or the entropy is zero. Entropy is the amount of disorder that is present, or the amount of noise that is present in the system, or you can call it the level of indecision that is present in the system. If the indecision is zero, noise is zero, there is no ambiguity, there is no say confusion, then we say that the noise is zero or the entropy is zero. So out of these systems, here you have the entropy as zero, here you have the entropy as zero. And what about this? Here you have, in this particular scenario, which is the fourth scenario, you have got 50-50, both the circles and the triangles. So what would be the level of noise here in the fourth scenario? In this one, what would be the level of noise or the level of indecision, or you can call it entropy, whatever you want to call it. It's 100%, okay? Or you can call it one. On a scale of 0 to 1, I'll say that the entropy or the noise is 1. That means that it's maximum. It's 0 here, it's 0 here, and it's maximum here, right? And what about this one? This could be any value between 0 and 1. So it's not 0 because it does not contain one shape. It's not 1 because there are two shapes here and all the two shapes are not equal in the basket. So it's not 1. So the indecision or noise is not 50%. Okay. So it's around 60, 60, 62, 62 or 63%. Okay, you can calculate that how many circles are there out of the total objects present here. So the total number of circles are, let's say if I also call this as a circle. Okay, so the total number of circles are 5 and there are 3 triangles. So 5 out of 3. So 5 divided, 5 out of 8. 5 out of 8. There are 5 circles out of total 8 objects. So 5 out of 8 is what I am getting as the noise level, something like that, right? Okay. So this is not, I mean, this is just an idea here. I'll let you know that how this noise is calculated in a while. And that is where these decision trees, I mean, the algorithm of decision trees comes out. It's not like this that you simply calculate the probability here. And calculating the entropy or the noise is a bit more challenging than simply calculating the probability. I'll let you know that how this is actually calculated. Okay. So now coming back to this decision tree, if I am asking the first question about age, why I am asking the first question about age? Why not workout? Why not junk food? The reason for that is that I would choose the first node, which is the root node, a variable that reduces the noise or entropy as close as possible to 0. Okay. So why I am choosing age? Because age might be able to reduce the noise in the system. more than workout and more than food. Okay, that's why I have got age at the root node. So age is primarily giving you more information compared to food and food and work. Therefore, the first question is about age. Okay. And the second question on the left branch, if it is yes, then I'm asking about food. Why not workout? The reason is that if the age is less than 30, in that case, food is giving me more information and is reducing the noise in the system more than workout on the left branch. Okay. Therefore, on the left branch, I am asking about food. And on the right branch, I am asking about workout. The reason for that is that on the right branch, workout is giving me more information or is reducing the noise in the system more compared to food. That's why I have a different question on the left branch. I have a different question on the right branch. Now, is this concept clear? Okay. Wonderful. So now let's see that how this noise is calculated. Okay, so let's just move on to the next slide and see that how this noise is actually calculated in a system. Okay, so before that, I'll just give you, so we call this as the root decision node. This is the decision node. This is the decision node, and this is primarily, this is not the decision node. This is basically what we call as the terminal node, okay, or the leaf node. The terminal node is primarily the node that gives you the final answer. So the leaf node in the CN trees gives you the final answer. Okay, so let's move on. Let's just move on to the next level. Next question. So this is the same nomenclature. I've given you what this nomenclature is. So, okay, the concept of entropy, I've already explained that concept of entropy. So here, if I draw the graph between the probability of occurrence of an event versus the entropy, and entropy is, remember, the level of noise which is present in the system. Okay, so if the probability is 0, or if the probability is 1 of a certain event, for example, this circle contains snakes, and the black snake is poisonous and the other one is not poisonous. So what would be the probability of poisonous snakes in this circle? The probability of poisonous snakes in this circle, there is no poisonous snake here, so the probability is 0. The probability of poisonous snake in this circle, they are all poisonous snakes, so the probability is 1. Okay, so this circle here and this circle here has a probability of 0 and 1 respectively. So is there any noise there? Is there any noise in this circle and in this circle? No. Therefore, the entropy for this circle and for this circle will be 0. In both cases, the entropy will be 0. And that you can see on the y-axis. So you have the entropy 0 here, you have got the entropy 0 here. And as you move along this particular path, you increase the amount of the number of poisonous snakes here. And if you move along this path, you actually reduce the amount of poisonous snakes. And here, right at the center, the poisonous and the non-poisonous become same. What is the probability of poisonous and non-poisonous in this case? The probability is 0.5, 50%. Okay. So when you have a probability of 50% of any event, then the probability or then the entropy at that particular level is 1. So here you have got the entropy, which is 1. Okay. So because it is the maximum indecision that you have got. The probability of poisonous as well as non-poisonous is 0.5. The indecision is highest, therefore the entropy is also highest, and we say the highest entropy is 1, right? And here, for example, the probability of poisonous snakes is 1 over 4.25, and the entropy is around this level. Similarly, here, the probability of poisonous snakes is about 3 over 4, right? 3 out of 4. And the entropy level is again around 0.7. Okay, so this is the relationship between entropy and probability. Okay. And the exact formulation for finding out the entropy is, we can represent entropy by H. So entropy is represented by a formula which is probability times log to the base 2 of the probability. Okay. So this is primarily, what do we have here? Probability times log of probability. Probability times log of probability. Just a minute, I'll be back in a minute. Okay. So I hope this is clear. If I give you the probability of something, you can calculate the entropy out of this using this formula. Okay, so for example, if I want to calculate the entropy of this event of poisonous snakes, so the probability of poisonous snakes is 1 over 4. That's the probability of poisonous snakes. And what would be the entropy? The entropy will be 1 over 4 log to the base 2 of 1 over 4. Okay. And if I calculate this, you can find out the level of entropy that comes out. It's very easy calculation, no difficult. Yeah. I hope this is clear, how to calculate entropy if probability is given to you. Okay. Okay, so let's move on to the next one. Okay, so here, this is the formula for entropy that I've just given you. Now, if you have got more than one classes, so here you have got, because the entropy primarily is to be calculated for all the classes that are present, for all the objects present in this particular circle. For example, here we are talking about poisonous snakes and non-poisonous snakes. So the entropy that I'll calculate, I've just calculated earlier the entropy for poisonous snakes. Okay, I can also calculate the entropy for non-poisonous snakes, and the entropy for non-poisonous snakes would be the probability of non-poisonous snakes, which is 3 over 4, and I'm talking about this circle. Okay, so this is the probability, and I multiply this with log of 3 over 4. Okay, so log of 3 over 4. And if I add the probability of poisonous snakes here, so this would be the entropy for the poisonous snakes. Okay, so this is 1 over 4. So this together will give me the entropy of this particular circle. The entropy of this particular circle. I have to calculate the entropy of both and add them, right? So that's why I have a summation here. Here C represents the number of classes that I've got. Okay, so you calculate the entropy for each class separately and add them. And this minus sign has to be there because of obvious reasons, because this answer would come out to be negative. Therefore, you have a negative sign here. So if negative multiplies, you get a positive answer. So the entropy would come out to be positive. Okay, so just to recap what I've just said, if I've got these circles and crosses in this particular case, if I want to find out the entropy of this event, how many crosses are there? 7. How many circles are there? 7. So the entropy can actually be calculated very easily because using this formula. So this would be 1 over 7 log 1 over 7 plus 1 over 7 log 1 over 7, because one would be for X and the other one would be for circles. Okay, yes. And in this particular case, in the second circle, you have got 7 crosses and you have got 4 circles. So the entropy for circles and crosses can be calculated and then added together. So this would be total number of okay, so sorry, the total number of the total number that you have got of circles and crosses in this particular case are 7 plus 4, 7 plus 4, which is 11. So the entropy for cross would be 7 over 11 log 7 over 11 plus 4 over 11 log of 4 over 11. Okay, so this is primarily you calculate. And in this particular case, you have got only 7 crosses. So the entropy in this particular case would be 7 over 7 log 7 over 7, which comes out to be 0. Right? I hope this is clear. Okay. Thank you. Thank you, Jihad, for your input. Thank you. Okay, so let's just go to an example now and see that how this actually works out. Okay, here I've got a table. And this table is primarily of playing football versus not playing football. Should I play football or not? I have to decide based upon some parameters, and those parameters are I've got outlook, I've got temperature, I've got humidity, I've got wind, and I want to decide whether I should play tennis or not. This is what I want to decide. And I want to develop a decision tree. The question is that should I ask the first question about outlook, temperature, humidity, or wind? Which question should I ask? Should I ask outlook? Should I ask temperature? Should I ask about humidity? If I ask a question about outlook, I would like to ask that is the outlook sunny, overcast, or rain? Okay. If I ask the question about temperature, then I would be asking question that is it hot, mild, or cold? Is it humidity high, normal, or wind is weak or strong? These are the questions that I want to ask. Why should I ask about outlook first? Why should I ask about temperature first? Why should I ask about humidity first? Why should I ask this question? Now I need to answer this. Okay. And Sanad, you and Jihad, you just said that we should ask about outlook. Why is that? Why you should ask about outlook? Okay. Now this is the question that we'll be answering. Okay. So let's just move on. So first of all, what you will actually be doing is that you will just first of all find out the entropy of the complete system. Okay. So we'll try to prove this, that outlook is that parameter that would reduce the noise. We have to prove it before we can't just make an assumption here. And this is how we'll actually do it. So for the first of all, just to forget about any question. First of all, forget about outlook, temperature, humidity, and wind. Just look at the last column and see that how much noise is present in the system. In this data, how much noise is present in this particular data. Okay, just have a look at the final column and see that you have got a mix of yeses and nos there. You have got some nos and some yeses. So is there noise present in the system? Forget about those other parameters for a while. We only focus on the last column. Okay, the last column. Just focus on this column and see, is there any noise present in this? The answer is yes. There is noise present in this because in the final column, you have got some no's and some yes. Okay, how many no's are there and how many yes are there? Right. So you can actually very easily count that. You can see that, okay, 1, 2, 3, 4, and 5. You have got 5 no's and the remaining are yeses. Out of total instances are 14. The total instances that you have got are 14 in this particular case. 14. So you have got 9 yes here and you have got 5 no's in this particular case. So before asking any question, let's find out the entropy of the system. Okay. Now imagine if they were all yes present here, then there was no entropy, zero entropy. Remember? There is only one class in the output, zero entropy. So do we need to develop anything? Because the answer in any case is yes. Whether it's sunny or temperature is cool or mild, every answer comes out to be yes. Therefore, you need not to develop anything here. The system is already noiseless. Or if they were all no's, the system was already noiseless. So you need not to find out anything. Your problem is already solved. I hope this is clear. So because now we have got a mix of no's and yeses, 9 yes and 5 no's. So let's find out the level of entropy, which is inherently present in the system. And excellent. Jihad, you have actually calculated that, which is 9 over 14 log 9 over 14 plus 5 over 14 log 5 over 14. And you put a minus sign there, and that would actually give you primarily the entropy level. And the entropy level for this particular scenario comes out to be, okay, this is what the entropy, the final answer comes out to be 0.94. So this is the entropy level that is present in the system without asking any question. Now, the next thing that we'll try to do is, now we'll see that if I ask a question about outlook, should, and if this entropy reduces, this entropy, the value of H reduces by asking about outlook, then how much it reduces? I'll find out that. Then I'll find out if I take temperature as at the root, or I ask about the temperature first, how much entropy will reduce from 0.94? And similarly, I'll do the same thing for humidity and wind. And I'll choose the variable that reduces the entropy the most as my first question. Okay. I hope this is clear. Okay. So for that, what I'll do is a very simple analysis. For that, what I'll do is that for the time being, I'll forget about these 3 variables. I'll just take the outlook column and the last column and represent that data in the form of that. In case of outlook sunny, how many yes and how many no's are there? In case of overcast, how many yes and how many no's are there? In case of rain, how many yes and how many no's are there? And I'll develop a small table out of it. Forget about temperature, humidity, and wind for a while. And I'll calculate these. I'll actually draw a small table. Okay, and that small table is here. So this is that small table which I have developed. Right. So in case of rainy, I've got 3 yes and 2 no's, total 5. In case of overcast, 4 yes, 0 no's, and 4 in total. In case of sunny, 2 yes and 3 no's, and in total 5. Total instances are 14. Remember, I'm not talking about anything else. I'm not talking about temperature, humidity, wind. I'm only looking at what? I'm looking at outlook. And what I'll do now is I can calculate the entropy for each of this event and add it together to find out the final entropy level. For example, I'll calculate the entropy for yes and no class for rain. then the entropy for overcast, then the entropy for sunny. So this is probability of rainy times. Okay, so and then I calculate the weighted average of that entropy, and the weight of that entropy comes with the probability of that event. So what is the probability of the event of rain? It's 5/14. Okay, so I calculate the entropy for yes and no for rain, and then multiply it with its weight, and that weight is 5/14. And this is what this P of rain comes in. So the entropy of rainy times the probability of rain. The entropy for sunny times the probability of sunny. The probability of the probability, not probability, the entropy. The entropy of overcast times the probability of overcast. Okay, so this is how I calculate the weighted entropy for outlook. Okay, so just keep this in mind, this table in mind, and just look at, first of all, look at what is present in the bracket. So what is present in the bracket? That is the entropy for rain, for rainy season. And because there are two classes, yes and no, you calculate it for yes, and you calculate it for no. So for yes, how many yes are present out of total 5? 3 yes. So 3/5 is the probability of yes in rain. And 2/5 is the probability of no in rain. Total instances of rain are 5. Okay, so you calculate this entropy and multiply it with the weight of rain. The weight of rain is 5/14. You do exactly the same thing for overcast. You do exactly the same thing for sunny. And you add it up, and that would give you the overall entropy of outlook. Now, is this thing clear? Is there anything you need clarification on this? Okay, so just to rewrite here, you multiply the probability of rain. I'll write down the probability of rain as PR times the entropy of rain. Okay, and then add to that the probability of overcast times the entropy of overcast, right? Plus you you add to that the probability of sunny times the entropy of sunny. And you already know how to calculate the entropy. The entropy of rain would be for yes and no. And for this row is actually used. Okay, for sunny, you use this row. For outlook, you use this row. Right? So is this clear, Sanad and Amir? Okay. Okay. So if I calculate this, the answer comes out to be 0.69. 0.6. And what was the original entropy in the system? 0.94, if you remember from the previous slide. Okay, so what is the reduction in entropy? The reduction in entropy. The reduction in entropy is called information gain. So the information gain or reduction in entropy for outlook is 0.27. So that means that you have reduced the entropy to 0.693, and the reduction in entropy is 0.247 for outlook variable. Now, we'll do exactly the same thing which we have done for outlook for all the other variables. Okay, so in the next case, what we'll be doing is we'll forget about outlook, we'll forget about humidity, we'll forget about wind, and we'll only take temperature column and the final column and repeat the same process as we did for outlook. and calculate the reduction in entropy for if we use temperature, right? Okay. And if I repeat this for all the variables, this is what I get. For temperature, the reduction is this. For humidity, the reduction is 0.152. For wind, the reduction is 0.048. For outlook, the reduction is 0.247. The highest reduction that we have got is for outlook. Therefore, the first question that I'll be asking is about outlook. So therefore, outlook comes at the root node. Okay. So outlook comes at the root node. So this is my first node on the decision tree. Outlook, sunny, overcast, and rain. And then what I'll do is that, okay, if I ask the first question, then what should be the subsequent question under sunny? Then what should be the subsequent question under overcast? Then what should be the subsequent question under rain? That is the next thing that I'll be doing. Okay. So for that, what you will be doing is that you will make subtables from this same table. So first thing is that you'll need to decide that, okay, what should come after this question on the left branch? What should come after that? Okay, so let's just try to answer this. So what you will actually do is, yeah. So what you will actually do is that come back to the same table. You just make a subtable out of it, and that subtable should only consist of sunny. Okay, this subtable should only consist of rows that in which outlook is sunny. So for you have got these 4 rows, 5 rows. So what you do is you only take this subtable for which outlook is sunny, because we are talking about the left branch for which you know that the outlook is sunny. And now you want to find out that if the outlook is sunny, what should be the next question? So for that, what you do is that you only take those rows in which outlook is sunny. If I want to find out what should come after rain, I will take a table that consists of only outlook rain, right? And so on. Okay, so what I'll actually be doing in this particular case is that I'll actually be making subtables out of the main table. So this is the subtable for outlook sunny. You see the first column is all sunny. Then you have overcast. And then you have rain. And now I'll see that, okay, in case of outlook sunny, what should be the next question? Temperature, humidity, or wind? If the outlook is overcast, what should be the next question? If the outlook is rain, what should be the next question? Is this clear? So I've made smaller tables out of that larger table. Okay, so and now what I'll do is that for each of these table, for this table, I'll repeat the same process which I've done earlier. Exactly the same process which I've done earlier. I'll repeat it for each of these tables and find out what should come next. So for example, for the first case, when the outlook is sunny, what should come after this? Should I ask about temperature, humidity, or wind? What should be the next question? So what I'll do is that I'll try to find out the entropy, because this is all sunny, so this is ignored. So I'll just take temperature from this table and I'll just take the final column here, okay, and find out the entropy for temperature, find out the entropy for humidity, find out the entropy or the information gain for this particular table, and then repeat the same process again. So for that, You will again start with the final column, find out the overall system entropy, then the entropy given temperature, entropy given humidity, entropy given wind. Exactly the same process which is shown here. You repeat the same process, find out the information gained for each of the variables. Okay. And the answer, let's say, comes out to be, in this particular scenario, if I ask about temperature after asking about sunny, the reduction is 0.5. If I ask about humidity after sunny, the reduction is 0.97. And if I ask about wind after sunny, the answer comes out to be 0.019. And this tells me that the highest reduction in entropy is with humidity. So after sunny, I should ask the question about humidity. So that's why humidity comes in. Remember, I've actually applied the same method which I applied earlier for outlook to humidity on that subtable. Right? Is this clear? And that's why humidity comes here. Similarly, the same thing will be repeated for overcast and for rain. Right? And finally, I'll come up with this final decision tree for that table that I've just shown you. So this is my final decision tree. Okay. Now, the important thing that I want to tell you here is that if you want to implement this in Python, it's a single line code. You don't have to do it manually. You just call a library, a function of decision tree, and that function will automatically calculate all the entropies and will give you the decision tree. So it's so easy to implement it in Python. And Waqar will actually let you know how to do that. And he has, I think, already recorded a video, and I'll upload that recorded video on the channel, and you can see that video, that how to use Python for the trees. So is this thing clear? Is there any question that you want to ask about these decision trees? Okay, wonderful. So I'll share the slides with you. The next slides, I'll just skip those slides, but that is for regression. If the output, remember, in this particular case, in this particular scenario, my output variable is a categorical variable. It's not a numeric variable. It's not a numeric variable. So what happens if I've got a numeric variable? If I want to develop a decision tree for numeric variables. So let me give you an example. Okay. So what if I want to develop a decision tree for this? Here I've got no yes and no. I've got numbers here. This is hours of play. So what shall I do now? Now, any ideas? What shall we do now? So earlier, when there was yes and no and categories, we used entropy. Here we have got numbers. So there we were looking for reduction in entropy. Here we'll be looking for reduction in standard deviation. Okay. And how is that done? That is actually shown in the next slides. I think it's very easy to follow these slides. You can actually go through this exactly the same way. First of all, the system level standard deviation is calculated, right? That comes out to be 9.32. Now we are calculating the standard deviation. You take the final column, take the average, okay, take the standard deviation. Okay. And then the next step would be that you find out the weighted reduction in standard deviation, the weighted reduction, SDR. We call it the standard deviation reduction. So you calculate the standard deviation reduction for each of the variables, outlook, rain, outlook, temperature, humidity, and wind. And the one that reduces the standard deviation the most is taken as the preferred variable, right? So the standard deviation reduction in this particular case for Outlook comes out to be 1.66. Whereas if I calculate the standard reduction deviation for all the other variables, using the method which is given on the previous slide, this method, applying the same method, you find that the maximum reduction comes with Outlook. Okay, so I'll take Outlook at the root for this particular variable again. And exactly the same thing is repeated, which I've just explained to you earlier. So I'll share these slides with you and you can go through these slides and they're easy. They're not difficult to interpret. Okay, so for the time being, what we'll do is that we'll move on to the next decision tree model. And there we'll end, sorry, decision tree, not decision tree, in fact, machine learning model. And here we'll end our discussion. And that is about the k nearest neighbor approach. It's a very simple, very standard sort of an algorithm. So for example, here I've shown you a graph. I've got, a plot in which you have got triangles and you have got these squares, the red triangles and squares. And I've got a circle and I want here, this is the new data point. And I want to find out whether this belongs to the class of circles or the class of squares. I want to label this new point. This is what I want. I want to label this. What should I do? How will I label it? What is the intuition here? What do you think? Anyone? How should I label it?
Assalamu alaikum.
Right.
According to the picture, you divide the space into three regions. And I think you will calculate each state. You have two triangles and the total number, and first the nearest one. In the mid, you have two square. According to the final number, and you will take a percentage.
Okay. Okay.
To decide.
Okay. Now, anyone else want to try? Okay, so the easiest way to do that is that I decide upon, I look at the neighbors of this circle. What are the closest points to this circle? If the closest points to this circle are triangles, then I'll label it as triangles. If the closest points to this is a rectangle, is a square, I'll label it as a square. Okay, but for that, I'll have to decide how many neighbors, how many closest point I have to choose. So let's suppose I choose 3, or let's say if I choose 3, let's say, okay. Then I look at the closest 3 points to the circle and then decide that what is the majority there. So in the closest 3 points that I've got to this circle, 1 is a square and 2 are triangles. So the majority belongs to triangles. Therefore, I'll say that, okay, this new point is actually a triangle. I'll label it as a triangle. Right? I'll label it as a triangle because I am taking 3 nearest points. Now, if I choose 5 nearest points, then this outer circle that you will actually see, that encompasses 5. In fact, k is, 5 in this case. So I've got 2 more, what you can say, squares. And then in that case, the majority belongs to squares. Therefore, this point would be considered as a square. Okay. So I look at the neighboring nodes or closest nodes or closest points and then decide. If it is a categorical variable, for example, in this case, I am labeling it as a triangle or a square, then I go for majority vote and find out that what majority is present in the neighborhood of this new point. Okay. If the majority is of squares, I label it as square. If the majority is of triangles, I label it as triangle. But for that, I have to decide how many points I have to take. And that is what is represented by K. And K, nearest neighbor, that's where the name comes from. K, I have to decide the level of K and then look at the neighboring nodes, the closest points to the unknown point. Okay, so I hope this concept is clear. Okay, and here I'll just elaborate this point again. I'll just elaborate this point with the help of another example. Okay, so for example, if I have got a star here and I want to label this, and if I take K is equal to 3, then 3 nearest points, I'll consider 3 nearest points, and these are the 3 nearest points. Therefore, this star will be labeled as a circle, right, or an oval. So this is what this new label would be. Okay. Now, if the new point is somewhere here and K is equal to 3, then these 3 points actually come into consideration. And all of these 3 points are rectangle. Therefore, it would be considered as a rectangle. Okay. So you look at your nearest neighbors and then decide. This is what K and N actually means. Okay. I hope this is clear. Now, this is the algorithm. What you do in this particular algorithm is that you load the data first, then you put some value of K. Okay. And then step 3 is repeated for all the data points that you have got. You calculate the distance of the new point from all the other points using any distance measure. For example, you can use Manhattan distance or Euclidean distance or any other distance. If it is categorical variable, you use the Hamming distance, right? You calculate that distance. Then you sort it. You take the top K points. Okay. And then you get the most frequent majority vote of those K nearest points, and you predict the class. You say that, okay, this is the class that I'm actually predicting, right? And you repeat this for any new point that you have got. Okay. Very simple algorithm. Again, if you want to implement this in Python, it's a very simple program that you have to write in order to estimate that. So here is a very simple example. If you have got age, height, age, and weight, and want to find out the weight of the person. Now remember, here we don't have a categorical variable. Remember, here we have numbers now. Okay. So in case of numbers, you take the average. Okay. So if these were numbers and I want to get a value here rather than the class, what I'll do is that I'll take these 3 points, I'll take their values and take an average and assign that average to this new point. Okay, so same is the case here. If I want to find out if the height of the person is 5'5" and the age of the person is 38, what should be the weight of that person? Okay, if I draw it, you will find that the new point comes here somewhere. If the value of K is taken as 2, then these are the 2 nearest points. Okay, this point and this point. And I simply take the average of these 2 and assign that value to this. Okay. Is this making sense? Yes. Okay. What about the others? Wonderful. So I guess now you are actually ready to do the uh, what you can say. So these are okay. Before I move on, these are the methods to calculate the distances. You can calculate the Euclidean distance. You can calculate the Manhattan distance, and if it is categorical variable, you can calculate the Hamming distance. So I guess these two methods are enough for our discussion. And we'll restrict ourselves to these two methods, and we'll be giving you a small programming assignment on these two methods, and one small written assignment which will be completing by 31st of July, or if you want to complete it early, you can complete it early and submit, and we'll prepare the result and submit to the Nija University. Okay. So any